Hello, students. This is Dr. Kelly Sexton again with part 2 of respiration. So I have a question for you. What do we breathe? Well, the correct answer is air. Another question. What is air? Well, air is a mixture of gases. The most common gas in air is nitrogen at about 78%. The next most common gas in air is oxygen, about 21%. Everything else, all the other gases, only equal a total of about 1%. Of those, the only thing we're really interested in is carbon dioxide at about 0.03%. Well, gases have mass, they have weight, and those gases pile up in layers around the earth, much like blankets. If you think about lying in bed and someone piling blankets on top of you, you begin to feel pressure, you begin to feel weight. Those gases exert the same kind of pressure, the same kind of weight. And at sea level, the weight is about 14.7 pounds per square inch, which is a lot. Well, we can measure this pressure. We measure it using something called a barometer. A barometer is a very simple device. All it is a tube with a vacuum in it turned upside down in a liquid. You can use any liquid you want. But to standardize things and to make the tube short, we use the densest liquid, which is mercury. So at sea level, 14.7 pounds per square inch are pushing down on this mercury and forces it up the tube. It forces mercury up the tube 760 millimeters. So 14.7 pounds per square inch is the same thing as 760 millimeters of mercury. 1 millimeter of mercury is equal to 1 torr. So 760 millimeters of mercury also equals 760 torrs. Each of those then equals 1 atmosphere. So here are 4 different ways of describing the exact same thing. As you move up in altitude, there's less and less air above you. And so when you're up on a mountain, there's less air above, which means there's less pressure. Use an analogy. Look at this. You can see these people are stacked up on top of each other. Well, it's obvious that the person on the bottom is going to have a ton of weight on them. They're going to feel a lot of pressure. If you look over to the right, you'll see the exact same thing. At the bottom, there are lots and lots and lots of atoms pressing down. So there are more atoms at sea level. As you move up the stack of people, there's less and less weight. If you're up at the top, there's hardly any pressure, any weight on that person. Same thing is true if you look to the right. As you move up, there are fewer and fewer atoms. When you're way up top, there are very few atoms of air. So if you look at this graphic, you can see exactly what that looks like. So at sea level, there's the greatest number of gas molecules and the highest pressure. As you move up the mountain, there's less and less and less and less, until eventually there's no gas molecules. Well, if we apply this same picture to a table and look at it, we can see exactly what happens when you move up. At sea level, remember the pressure is 760 millimeters of mercury, including oxygen and so on. If you look to the far right, you will see that at that pressure, about 98% of our blood becomes saturated with oxygen. As you move up in altitude, look what happens. At 10,000 feet, only 87% of our blood. At 18,000, 72% of our blood. At 22,000, 60% of your blood. Most planes fly between 25 and 35,000 feet. Look how much oxygen there is. The pressure is only around 200 or so, and only about 9% or less of your blood is saturated with oxygen. That is way too little for you to breathe. That's why they pressurize the cabin of airplanes. The exact opposite is true if you start going underwater. Water is much denser than air, and so you don't have to go very far for it to become very, very heavy and dense. If you travel down about 33 feet, the pressure doubles. So we're at 2 atmospheres. Another 33 feet, we're at 3 atmospheres. Another 33 feet, we're at 4 atmospheres. That pressure pushes on you. It also pushes on everything else. If we take a balloon at the surface and look at it, look at what size it is. And look to the right, and you'll see how spread out the air molecules are inside it. But as you move down, look what happens to the size of the balloon. It gets smaller and smaller, and the molecules become more and more compressed. At 99 feet, it is only 1/4 the size that it was at the surface, and the density is 4 times what it was at the surface. That means that a bubble of air is very, very tiny at great depths. At 6 atmospheres, it's a tiny, tiny bubble. And this person at 6 atmospheres is breathing that air. Well, if those gases are allowed to expand as this person rises forward, look what happens. And if the person were to move up very, very quickly, this tiny bubble would turn into a huge bubble and could cause things like hemorrhaging throughout the person's circulatory system. This could cause a condition called the bends, and that can result in death. Well, to truly understand what's going on with gases, we have to look at gas laws. So we're going to look at several different gas laws. The first one we're going to look at is one called Dalton's law. And so look, these are gases. They're inside a container and they exert a pressure. So in the first one, we see oxygen exerting a pressure. Oxygen is the only gas in that container, and so it's the only gas exerting that pressure. Same thing is true in the second picture where we see nitrogen. If we put both of them in there at the same time, they're exerting a combined pressure. That combined pressure is equal to their individual pressures. What Dalton's law says is that these individual pressures contribute to the total equal to their percentages. So if we look at the total gas pressure, all it is the sum of the individual partial pressures. In this graphic, we can see all the different gases that contribute to air. And right below that, you can see their percentages. Remember, nitrogen is about 78% of air, oxygen is about 21%, carbon dioxide about 0.03%. Each of these has a partial pressure, and that partial pressure is equal to their percentage times the total pressure. So the total pressure is the sum of the pressures exerted independently by each individual gas in the mixture. And since it's the sum of these, the partial pressure is directly proportional to its percentage in the mixture. So if I want to know what the partial pressure of nitrogen is, it's quite easy to figure out. I multiply the percentage times the total pressure. Remember, at sea level, the total pressure is 760 millimeters of mercury, and that nitrogen composes 78.1% of the total. So if I want to know the partial pressure of nitrogen, I multiply 0.781, 78.1%, times the total pressure at sea level, 760 millimeters, and I come up with the partial pressure of nitrogen at sea level. So the partial pressure of nitrogen at sea level is 599.6 millimeters of mercury. The exact same thing is true for oxygen. Remember, oxygen composes about 20.9% of the total. At sea level, the total pressure is 760. If I want to know the partial pressure of oxygen, I multiply 0.209 times 760. And at sea level, the partial pressure of oxygen is 159.6 millimeters of mercury. Same thing is true for carbon dioxide. Remember, it's 0.03%. So I multiply 760, which is the total pressure, times 0.0003, and I come up with 0.23 millimeters of mercury. If I add all of these together, I should come up with the total pressure. Let's look at another law. This one's called Boyle's law. What Boyle's law says is that pressure and volume in a container are related to each other. And they're related inversely. What that means is that if one goes up, the other one must go down. If the other one goes down, the other one must go up. So if I vary one of these, the other one varies automatically. If I vary the volume, pressure will change. So if I increase the volume, automatically pressure goes down. If I decrease the volume, automatically pressure is going to go up. So if I look at this graphic, you can see that there's two containers here with a plunger. Now they have a constant temperature. You can see how many molecules are in there, and if you count them, they're the same in both sides. So we're not changing the temperature, we're not changing the amount of the gas. What we're going to change is volume. So going from A to the other one, we can see that the volume decreased. And if you look at the gauge, automatically pressure increases. So again, if we decrease the volume, pressure goes up. If we decrease the volume, pressure goes up. In this case, the volume is 1 liter, the pressure is 1 atmosphere. So if we look at that, that's what our initial situation is. But I'm going to push down on the plunger. Now the volume is 1/2 liter. What's going to happen is the pressure will go up by a similar amount. So we went from 1 liter to 1/2 liter. The pressure is going to go from 1 atmosphere to 2 atmospheres. 1 times 1 is equal to 2 times 1/2. Boyle's law. Again, if I increase the volume, pressure goes down. If I decrease the volume, pressure goes up. This line, this graph, shows you the relationship between the two. So get another one. This one's called Henry's law. Henry's law talks about gases dissolved in liquids. Look at the situation here. We have a chamber with gases in it. It's also got a liquid in the bottom. As the gases bounce around, sometimes they hit the surface of the liquid and become dissolved in it. If we change the pressure by changing the volume, remember Boyle's law, if we push down on this, pressure is going to go up. Well, as the pressure goes up, more and more of that liquid is going to come in, be in contact with our gas. And so more and more of the gas is going to become dissolved in the liquid. So what Henry's law says is that the amount of a gas dissolved in a liquid is proportional to the pressure of the gas over the liquid. So look, on the left, we have a big volume, which means low pressure. Very few of the molecules of gas are going to become dissolved. But on the right, we push down, we decrease the volume, so we increase the pressure. More and more of that gas is in contact with the liquid, and more will become dissolved. Higher pressure equals more gas dissolved. Higher pressure equals more gas dissolved. A good example of this is what happens with a soda. A soda only has all of that gas dissolved in the liquid because it was bottled under high pressure. So they took the Coke syrup or the Pepsi syrup or whatever it was, and That's the liquid. And over that, we put high pressure carbon dioxide. And so lots and lots of the carbon dioxide becomes dissolved in the liquid. And then we seal the container. Once you open the container, though, the pressure immediately falls and the gases begin to come out of the liquid. And so if you leave this open soda can long enough, almost all of the gas will leave the liquid and the soda will become very flat. So Henry's law says that the amount of a gas that will dissolve in a liquid depends on its pressure. There's another thing it depends on too, and that is its solubility. Some gases are very soluble and easy to force into a liquid. Some are not so easy. Of the three that we're interested in, carbon dioxide is the most soluble. Oxygen is only about 1/20th as soluble as carbon dioxide, whereas nitrogen is almost completely insoluble in plasma. It is very, very difficult to get it to go into water. So the only time that nitrogen really, really becomes dissolved in a liquid is when we have very, very, very high pressures. Remember our person who's swimming at 6 atmospheres of pressure? There's tons of pressure pushing all of the gases into the liquid of your blood, including nitrogen. So at very large depths, nitrogen will also dissolve in your blood, and it can cause symptoms that make one person feel almost drunk. It's called nitrogen narcosis. It can also create a problem when you rise to the surface because those dissolved gases again bubble up. They become huge gas bubbles and can cause things like hemorrhages and so on. Let's look at another law. This one's called Charles's law. In Charles's law, all it says is that warm air occupies more space than cold air. And this is very, very easy to recognize in a hot air balloon. So if you start with a hot air balloon on the ground, there's air inside the balloon. And what we do is we heat it. We're not pumping more air in there. We're heating the air that's already in the balloon. As you heat it, it spreads out. And air that's spread out as it expands is lighter because there's fewer molecules per certain amount. And so when you heat it up, look what happens. Those molecules bounce around much, much faster and volume increases. As you heat it up, they bounce around, volume increases. This is easy to illustrate. You can take a gallon jug with nothing but air in it, tie a balloon on top of it, and put the gallon jug either in ice water or warm water. As the air in the jug changes temperature, it's either going to increase the size of the balloon because it's spreading out, or it's going to decrease the size of the balloon because the air is becoming more compact. So, these are those laws. If I were you, I'd pause right here and go back over each one of these laws until you understand them. Now that you understand gas laws, we can talk about how air behaves and how gases behave in the respiratory system. Don't forget that air is a mixture of gases. Air will flow. Air always flows from high pressure to low pressure. So if you took a drinking straw and you blow through it, you're creating a higher pressure in your mouth, and that forces the air out the other end. If you took the same drinking straw and sucked into the drinking straw, you're creating a low pressure, which means it's lower on your end than the outside. Air is going to move one way or the other. Get a drinking straw and see this for yourself. You can also take a balloon and blow it up, As you blow it up, you're increasing the amount of air, the pressure on the inside. If you let go of it, higher pressure air on the inside is going to force its way out. Another property of air and gases is that gases move, they diffuse. Well, diffusion always only happens in one direction. It happens from high concentration to low concentration, or from high pressure to low pressure. Gases diffuse independently of each other along their own gradients. So in this case here, diffusion is moving from high concentration to low concentration. Let's not forget that we're talking about respiration. Remember, that's 4 different processes. The first one is ventilation. Ventilation, remember, is moving air into and out of the respiratory tract. External respiration. This is gas exchange that happens in the lung between air and blood. Internal respiration, which is gas exchange that happens between the blood and the tissues. And then finally, cellular respiration, which is what we're not going to talk about, although it might be most important. That's using the oxygen in the process of producing ATP. So these are our processes, and we're going to talk about each one of them. Let's look at ventilation. Ventilation is moving air into and out of the respiratory tract. In other words, it's 2 phases. Air flowing in, that's called inspiration. Air flowing out, that's called expiration. Everyone take a breath, and you can see exactly what's happening. As you breathe in, air flows in through your mouth and nose. And then when you relax, air is going to flow out through your mouth and nose. We do this over and over and over. The average person breathes somewhere between 12 and 15 times a minute at rest. Well, in order to understand it, remember we have to think about pressures. There are actually 3 pressures that we need to worry about. One is atmospheric pressure, or the pressure in the room where you're located. Another is the pressure inside the alveoli of the lungs. There's also a pressure in between the 2 pleura in the pleural cavity. So we can see those pressures. Atmospheric pressure and intrapulmonary pressure are always exactly the same, or they're in the process of becoming the same. So at sea level, remember what atmospheric pressure is? It's 760 millimeters of mercury. That means it's 760 outside, which is the room you're in, but it's also 760 inside your lungs. If it were higher in the lungs, air would move out until they were equal. If it were higher outside, air would move in until they were equal. This is possible because of the glottis is usually open. However, there's another pressure, and that's the pressure between the 2 pleura. The pressure between the visceral pleura and parietal pleura, or the pleural cavity. This is called intrapleural pressure. This is a sealed cavity, and so it's not subject to atmospheric pressure. It's also a cavity where we typically adjust the pressure, and typically we adjust it to be about 4 millimeters of mercury less than atmospheric pressure. So if you are at sea level, remember atmospheric pressure is 760, over time you will adjust intrapleural pressure to be about 4 less than that, or 756. If you change your location, over time you'll change the intrapleural pressure. With every single breath, these pressures are going to change. But eventually, the pressure inside the lung is always going to equalize itself with atmospheric pressure. Remember, they're always equal or in the process of becoming equal. And then intrapleural pressure is always about 4 millimeters of mercury less than the other two. This intrapleural pressure is important because it keeps our lungs partially inflated. Remember, it's about 4 millimeters of mercury less, which means that our chest cavity is slightly negative, slightly sucking on the lungs. When you suck on something, the same way that you suck air through a straw, it makes the lung inflate. To remove that 4 millimeters of mercury, what's going to happen is the lung will collapse. So let's look at ventilation. So ventilation is one inspiration followed by one expiration. We need to remember Boyle's law. Remember, Boyle's law said pressure and volume are inversely related to each other. So if we increase the volume, automatically we're going to decrease the pressure. If we decrease the volume, the opposite's going to happen. So during inspiration, what's going to happen is muscles contract. The muscles that contract are called inspiratory muscles. And these muscles increase the volume of the thoracic cavity. As thoracic volume goes up, pressure is going to go down. And as pressure goes down, it's going to be lower than the pressure outside. And so air will flow into the lungs. This is going to continue until the two pressures are exactly the same. So if we look at this graphic, the far left is a neutral position. And look, the pressure in the lungs and the pressure outside are exactly equal. But when the inspiratory muscles contract, this middle picture shows what happens. The chest cavity gets wider. It also gets longer. So volume goes up. Pressure is going to automatically go down. Now the pressure on the outside is higher than the pressure on the inside. And so air will flow in. It will flow in until the two pressures are exactly the same. Once you decide to breathe out, what happens is the inspiratory muscles relax. All of the muscles relax, and so the volume is going to decrease. Again, using Boyle's law, when volume decreases, pressure goes up. And now the pressure on the inside is higher than the outside, and so air flows out. It's going to continue until they're equal to each other. So if we use the graphic again to the far left, here's the end of our full inspiration. There's no air moving because the pressures are exactly the same. But then what's going to happen? Those muscles relax. So the chest cavity is going to get narrower and shorter. Volume goes down. When volume goes down, pressure goes up. Now the pressure is higher on the inside than the outside, and so air flows out. And then the previous one is going to repeat. It's going to happen over and over and over again. Take a second and monitor your own breathing and see this happening. You can see your chest rise and fall. That's because the chest is getting wider and bigger and then getting smaller. And monitor what's happening to air. Most of the time when we expire, it's passive. All that happens is muscles relax. We can also choose to force air out. Well, the only way we can do that is to make the cavity even smaller than it normally is, and that requires muscles. These muscles are called expiratory muscles. The expiratory muscles make the thoracic cavity volume decrease even more than normal. And so pressure is going to go up even more than normal. And so air will be forced out until the two pressures are the same. So if you choose to do something like this, you're forcing air out by decreasing your volume more than it normally does. If you do this over a period of time, you actually get quite tired because those muscles, the expiratory muscles, are actually not very used to being used very much. Most of the time, our expiration is just relaxing muscles. Remember, when air goes out, the lungs are emptying. That includes those little alveoli. Well, the inner surface of the alveoli is wet. And when two wet surfaces come in close contact, they tend to stick to each other. Think about if you wash your car and wax your car. And if there's water that beads up on that wax surface, if they get near each other, they're attracted to each other. Water has a surface tension. Well, the only way to prevent those little tiny alveoli from collapsing is to decrease this surface tension. And that's exactly what surfactant does. Remember, surfactant is made by these type 2 cells. It coats the inner surface, reducing surface tension so the alveoli don't collapse. Without that surfactant, this cohesiveness, the surface tension of water causes those alveoli to collapse, and they're very hard to reinflate. We don't make surfactant in utero because our lungs are not full of air. However, near the end of pregnancy, usually about the 7th month, we begin to make surfactant. If a baby's born before that time, there is no surfactant. And so in very premature babies, we see a condition called IRDS, Infant Respiratory Distress Syndrome, which means with every single breath, all of the little alveoli in their lungs collapse. This makes it very difficult for these premature babies to breathe. And before we had a way of fixing that, most premature babies died of exhaustion just from trying to breathe. Now we breathe for them. Oh, we put them on a machine where we have positive pressure. And so the positive pressure forces air into the lungs. However, this is very, very delicate. Has to be controlled very, very well. Otherwise, this positive pressure will cause all those little alveoli to rupture. End of part 2. Please continue on to part 3.